what I'll go over today is the material to do with water. So, why are we so interested in the water? And it's really because water is highly important to biological life, and it's important because the things that it carries. And one of the key things that it carries that we're studying is going to be this hydrogen ions, which are important because they get readily released into the water, but also because they're readily accepted by lots of groups in the water. They're released in the water by acidic groups, and then they're taken up in this aqueous solution by the basic groups. And so just basic acid-base chemistry. An acid is a proton donor, and a base is a proton acceptor. Let's see this. I'm going to mirror this camera. There we go. Okay. And a base is a proton acceptor. So what is a proton? What am I talking about here? So I mean, I guess you know what I mean when I'm talking about proton in the electrons, protons, neutrons. You get that. Am I talking about protons in water here? Now, and why am I drawing it as H plus? You think of just your proton that you're starting with. I just think of hydrogen. Right, hydrogen. It's got an atomic number of 1. Atomic number of 1. It's got, if we're looking at the protons, neutrons, electrons profile in it has 1 proton. Protons have a positive charge. It's got 0 neutrons, and it's got 1 electron with a negative charge, and these are balancing out. And the number of electrons in an atom is always equal to the number of protons. So we covered that. But if we were to have a chemical reaction with in water, where perhaps you have an acid, and let's just say we just give a generic, well, let's start even more with something like hydrochloric acid. Okay, what happens is that the electron will get donated to the. It's quite happy to split apart, and the electron will from the hydrogen, that 1 electron will go across to the chlorine. You end up with H plus and Cl minus. And if we've got a PNE of what hydrogen is, you take away the electron, just a proton. So that's why sometimes we just call hydrogen just a proton. And this, for example, to give another example of a weak acid, and I'll just do the R as just being any kind of alkyl group, like a carbon chain. And you've got like a carboxylic acid, which is a COOH group. And that's going to dissociate the electron that hydrogen has that is being shared in this oxygen-hydrogen bond. Being shared. Well, what will happen is that it will give away that electron, or the oxygen will just completely take it, and it will dissociate. And it's an equilibrium, but I'll just draw it as an arrow, and you'll get the R CO negative plus the H plus, so the proton, and it will dissociate. So here, this group here is donating hydrogens. It's letting them loose. It's donating them. And so this is why we call it an acid. Now, in water, it's releasing this freely into the water, and so it can float around. So in reality, what happens is that the water, it will react with the water, and the water kind of acts like a base. Remember, a base is a proton acceptor. So water will kind of act like a base and will soak up that hydrogen. And what you'll find in solution is that you'll have a hydronium ion, H3O, in water. And so this hydrogen, this proton, really important to life because it takes part in a lot of biological reactions. It takes part in acid-base chemistry reactions, which are kind of really integral and important to life. It takes place in, for instance, when we're talking about proteins, and you might have a basic group of a protein, of an amino acid in a protein, and it will bind to that, it will react to that basic group and form like a base. And for instance, with the amino acids, you've got the amine group, but then it'll take the hydrogen and it'll become NH3 plus. That's something that you see in amino acids for the part of the structure of amino acids. So if it participates in a whole bunch of chemical reactions, it's important in oxidative phosphorylation, which is a chemical reaction in the mitochondria, which is used in making energy. It's how you make energy, how you make ATP. So this little proton here, it reacts with a whole bunch of different things. It's quite reactive, and those reactions are often very important to life. And there's a bunch of ways in which it can be made, such as things dissociating various. There's lots of these acidic groups. There's lots of these that they're all kinds of acids. Bear in mind, an acid is just a proton donor, a hydrogen ion donor, a proton donor. And there's lots of acids. There's tons of them. And there are also lots of these hydrogen ions being released into aqueous solution. Then there's lots of these hydrogen ions being taken up by various bases, hydrogen ion acceptors. And it's quite reactive, and this is happening all the time. And lots of this happening. And so because of that, it's going to be quite advantageous to try and measure it. Okay, and that's what this is all about. When I'm talking about the pH, the Henderson-Hasselbalch, all of that stuff, it's talking about measuring the concentration of this, because it's really important to life, for being able to measure it. The rate at which it's being made by all of the chemical reactions in the body, or just in the universe, the rate at which it's being taken up because it participates in all those chemical reactions. And so all of this stuff, pH, Ka, Kw, Henderson-Hasselbalch, all of it is just about different ways of measuring this in different situations. That's what it's all about. And then this builds on later to do with the stuff to do with metabolism and respiration, how we make energy. It builds on the stuff later on with the structured proteins, because it modifies amino acids, which modifies the structured proteins. So this is all why we start with this, and we move on to later for the rest of the stuff. So let's start with how we go about measuring these hydrogen ions. And we can start out with water. So, because I don't have lecture slides, I've just got some notes to make sure I don't forget anything and I cover everything. So yeah, that's so advantageous to measure. So let's move on to water being the medium of life. Water is where these hydrogen ions get released. Water is where they react with bases and things in our biological setting. So let's start out with water. So H2O. Now, part of the reason of what makes a lot of these things, such as carboxylic acids, part of what makes them so reactive is to do with oxygen, and oxygen being electronegative. And because oxygen is electronegative and wants to take up electrons, it's greedy, it wants to take up electrons. You guys comfortable with the idea of electronegativity? Electronegativity, just to really just make sure to frame it and then clearly define it. It is the tendency of elements to pull on electrons. It's the tendency where when they're in a chemical bond to pull on electrons, so to take a greater share of the electrons. So, and because of that, because the hydrogen has only got one electron, when it's chemically bound, sometimes that electron can be taken up completely by the oxygen, freeing the hydrogen, which is now essentially just a proton, to be released into the solution. And so here we have that same thing, H2O, hydrogen bound to the oxygen, and the oxygen's kind of greedy, it's pulling on the electrons. And so what you actually get spontaneously in equilibrium, and equilibrium doesn't mean that nothing's happening. It just means that something is being generated as fast as it's being taken away. Okay, so it's constantly going back and forth, but it's at a constant rate, so that the two levels are the same. So if you constantly in equilibrium, you will have this. Breaking up. And we can reflect these as being, put these in square brackets, because we can say that there's all concentrations. It's all just something that's all just there in the water, diluted. Now, These, like I said, this is all in equilibrium, and so it's in constant flux, but it's out of balance. But so if you've got like a seesaw, you've got the fulcrum. It's at balance, which means that the rate of this one being pushed down is the same as the rate of this side being pushed down. But the thing is that just because it's in equilibrium and just because it's balanced, doesn't mean that this fulcrum has to be in the very center. That fulcrum can be a different place within the balance. And if it's at a different place within the balance, for instance here, that means that you're going to need a lot more of this. There's going to be a lot less of this. But they're still balanced. But you have more of this, less of this. And that's the case in water. For instance, water, this ionization, because you create ions, so it's called ionization. This ionization is balanced, but it's not an equal balance. And so you have a lot of water. It doesn't ionize very much. You only get a very, very small amount of the ions being produced, only a tiny amount. And so the position of the fulcrum is dictated by your values K. K is just and it probably comes from some wild German in the 18th century who discovered this kind of stuff. And it's probably German constant is with a K or something, and so they just call it K. But with these equilibrium constants, it doesn't matter what you're talking about, what type of chemistry, biology, physics, any kind of science. When you have an equilibrium, where the fulcrum is, so deciding how far across, whether or not you have more on this side, more on that side, is dictated by the letter K. And in this common equilibrium is quite often use KEQ. You're probably thinking, why didn't say KA? That's because that comes later. That's the EQ bit. That's just really just like a little note to help in scientists in conversation know what we're talking about. Because if it was all KEQ, then we just get really confused. So what we do is that sometimes we call it EQ, sometimes we call it A, sometimes we call it B, sometimes we call it W, call it different things to make it easier to communicate. But often it doesn't actually work that well because there's multiple KAs that mean completely different things. You have the association constant, you have the acid constant, and it gets confusing. But ultimately, it's just K. I mean, it's just the K you do. Now, let's say, first of all, let's do some math now, and let's figure out. So I was saying that we want to know, it's advantageous to know the concentration of the hydrogen ions because they participate in all these chemical reactions. And this is something I want you guys to be able to understand. Like I can't let you leave biochemistry unless you're able to measure the hydrogen ions in a solution because they're so integral to biology and chemistry and health and things like that. So let's start with just measuring them just here with in water. Let's just measure if you just got some pure water in a flask, what's the concentration of hydrogen ions? So the first thing is that we can rearrange this equation to make this the subject. That's what we're going to do so that we can find out what the concentration is. So the way that's rearranged is that it's KEQ, that constant, equals H plus OH minus over H2O. So the concentration of the products divided by the concentration of the starting material. And that equals the KEQ. And that kind of makes sense because if we're trying to work out how far over, whether or not you have more of the products or more of the starting material, well, KEQ is essentially a ratio. And what's this? That's a ratio, isn't it? That's a ratio of products to reactants. Thank you. So it's KEQ is just like I was saying, it's the measure of which way over it is, and so that's what it is. Now, what we can do, we can plug in some numbers, some known numbers, in order to figure out the concentration of H plus. So KEQ for this reaction has been figured out using in the past, a physicist that passed on electrical current through pure water. And I've worked out by doing that, they've worked out the ionic constant. They've been able to work out the KEQ for this reaction. And the KEQ is, I'll do it underneath, 1.8 times 10 to the negative 16. And then we want to know H plus, and OH minus is just something that we're just going to have to, we haven't solved for that yet. But we also know the concentration of water, which is weird. Talking about the concentration of water in water, it's like as an odd concept. But by knowing the weight of water and the physical weight of water, like when you put it on a scale, but also the molecular weight of a single molecule of water, because it's H is a molecular weight of 1, oxygen has a molecular weight of 16, but you've got 2 hydrogens, so the H2O has an overall molecular weight of 18 grams per mole. And then if we were to take away how much pure water weighs, we can feed that into an equation, into the concentration equals the number of moles over volume, the number of moles equals mass over molar mass. We can feed that in to find out what the molarity of pure water is. The molarity of pure water is 55.5. Now, let's now work with this. And this is going to be applied to weak acids as well, but we'll do it first of all just with water. So we can rearrange this equation for 1.8 times 10 to the negative 16 multiplied by 55.5 is equal to the ionic products. And then going by, if you guess what number is just about to, well, this is a rhetorical question, but I'm saying to you guys rhetorically, guess what number is about to come up? And you would have heard this number before. And then you'll be like, this is where it comes from. Now, these two multiplied, so these two multiplied will give us the concentration of the ions on this side. These two multiplied is 1.0 times 10 to the negative 14. There we go. And that gives us the concentration of these. And this number here, you guys remember, what's the label for this one? The label, like the name that we give it. No, not quite. It's KW. So it's the KW of water, and that's why the KW of water, when it's brought up, is referring to the concentration of ions in pure water, because this is pure water. These are the ions. The concentration of ions in pure water is 1 times 10 to the negative 14. But that gives us this number. But then how do we get onto the protons, the concentration of hydrogen ions?
And I got this one wrong because you actually was the case of I think it was 08, and I said I put the case of water. But if I'm not mistaken, would it be like 1 times 7 or 08?
That's right. Yeah.
Okay.
That's right. So this is the KW. This is the KW.
Mm-hmm.
But the KW is just the number is a total number of the total concentration. So it's got units of I should say it's got units of moles squared. So it's the total concentration is 1.10 to the 1.0 times 10 to the negative 14 moles squared. So that's the units for the concentration of this. But if we want to get the concentration of just the hydrogen ions, well, what we can do is that, and so I might ask question is, what is the KW of water? What's this? But that is not saying what's the concentration of this or what's the concentration of this. It's a concentration of everything. but I might ask the individual values. Now, because when this ionizes, it goes from 1 to 1 to 1. These are in an equal ratio. It's not like you get, for instance, let's say in this wild vacuum world, you would get this. Well, this would be a 2 to 1. But that's not what it is. It's a 1 to 1. Because it's a 1 to 1, we know that whatever this is going to be the same number. They're going to be equal. And so there's two ways of resolving that. You can either do it as in these are x, and therefore it's x times x, which equals x squared, and then you can just find the square root, or you can just divide it by 2. Either is fine and it gets the point across. So I guess x squared is a little bit more mathematically correct, and is going to there may be some advanced applications that may be a little fiddly, and you may trip up on them. So it's best to do it as the square root, but divided by 2, because it achieves the same thing. And that will give us the square root of 1 times 10 to the negative 14, or the same as 1 times divided by 2. It's going to give 1.0 times 10 to the negative 7. That equals the hydrogen ion concentration. So that's the concentration of hydrogen ions in pure water. As we want to know this because it participates in biological chemical reactions. There's various things that donate it in solution, various acids. There are various things which take it up in solution. A whole lot of chemical reactions that can occur. So we want to know this. We want to know it in lots of applications. Now, this number, 1 times 10 to the negative 7. Bit awkward to deal with. It's just kind of it's fiddly to talk about. It takes me a long time to even to say 1.0 times 10 to the negative 7. That's like it's a bit of a mouthful. So sometimes it can be difficult to communicate this number. And for instance, it's on a really long scale. So it can go, if this is the kW of water, and if I was to introduce an acid into water, then I'm changing the ion concentration. And in theory, I could introduce enough acid or enough base to go anywhere from 1 all the way across. And I'm going to illustrate my point and make it super clear. From 1, well, let's say you go 1.0 times 10 to the 1, which is 1. No, it's not. That'd be 10. But let's just keep it simple. 1.0 all the way across to 1.0 times 10 to the negative 14. That's a really big scale. 14 zeros. That's a really big scale. That's kind of awkward to work with sometimes. It's difficult to communicate. It's awkward to work with, and that's just with the zeros. This one, of course, can be 1.2, 1.65, 1.8523. It just gets really awkward and difficult to work with. So what do we do? How do we make that number? How do we make that number easy? So how do we make this the number easier to work with? And all we do is that we just transform it. We just transform it, and when we transform it, it's a different number, but it's kind of the same number, but looking at it through a different set of glasses. That's not mathematically true, but for the terms of like real world applications and the way that humans interact with reality, effectively all you're doing is that you can just transform that number, put it into a different set of glasses to make it easier to work with. Because we're working at something to the base, and it's to the base of 10. Well, the simple things that we can just take the log of it. Take the log of it, and then you just all of this stuff over here, all of that stuff, just get rid of it. You just take the log of it, and then it just makes it easier to communicate. Now, because this is a negative number, if we take the log of it, then it's gonna give us a weird number. All we do instead is that we just take the negative number. If we took the log of 1.0 times 10 to the negative 7, it would give us negative 7. But let's not work with negative numbers. We're trying to make things easier, right? We went to the bother of making it log to make things easier, or it's just generating a negative number. So let's instead make the negative log. That gives us 7. 7 is a lot easier to communicate than 1.0 times 10 to the negative 7. It's much easier to use in mathematical equations, and chemists and biologists are not mathematicians. We may do math, but we're not mathematicians. We want to be the practical application. Easier way of making this practical application is to transform the number. These are still communicating the same thing. They're still the same thing. They're not, but they're still kind of the same thing as scientists. It's just that we just made it easier to handle. And okay, that's the next thing I was going to say is that this again is so what we have is the hydrogen ion concentration equals negative log 7. But let's instead, what we can do is that mathematicians say that instead of saying negative log, the negative log is just given the letter P. So the negative log of the hydrogen ion concentration is 7. And that's all it is. This pH is just P is just mathematician shorthand for negative log, and H just means concentration of H. Just a negative log of concentration of H. And in water, that is pure water on its own, that is 7. So are you guys comfortable with that? So now I'll move on to applying that to some the questions. And these questions will be worth a lot of marks. Let's start with first of all, strong acids. So strong acids are things that typically are ionic compounds that completely dissolve in water to completely separate into their 2 parts. And their 2 parts are going to be the cation. Remember, cations are positively charged. The cation, hydrogen, proton, and their anion, the negative anion, which would be the conjugate base was referred to as the conjugate base. It's referred to as the conjugate base because it's lost its hydrogen. It would actually, in a way, be quite happy to take up a hydrogen, and things that take up hydrogen are referred to as bases. So this referred to as the conjugate base. Now, like I was saying, so a strong acid is going to completely dissociate water, similar to how we have like table salt completely dissociates into Na and Cl. A strong acid is going to do the same. There's a few typical strong acids, things like hydrochloric acid, sulfuric acid, nitric acid, HNO3 nitric acid. Another example would be H2SO4, sulfuric acid. These are all strong acids. I won't use the example. I will tell you guys in exams. I will tell you guys it's a strong acid. But I'm just saying these are very typical common strong acids. They completely dissolve. I will never use H2SO4 as an example because it's more complicated. Because it might be more complicated. Not quite. What's the thing that we want to measure? That's it. Because it's got 2 hydrogens. So it can actually go twice. Actually go twice. And so it gets a little bit more complicated. Well, in fact, I'm not going to ask an example of it. And actually, it's not actually that much more complicated. I'm not going to ask it as a question, but it's just That's not what I want. I want you guys to get the concept, not to. There's a special rule that you'll have to apply to this, and it's a really simple special rule, but I don't want to keep adding on to the burden of learning all this material. Rather, just like you guys to be able to understand concepts, or maybe it might be something that I put in like a 3-mark question, and if you forget the special rule, then you get 2 of the marks, but you get the 3rd mark for getting the special rule, or something like that. But anyway. So let's go with hydrochloric acid, nice classic example. We're going to dissociate completely. So just draw an arrow to H plus and Cl minus. Now, what's the thing that we want to measure? Hydrogen, right? We want to measure the concentration of this. Now, if this completely splits into these 2 halves, we can do a, let's say like before, and then before and after dissolving in water. Now say that the concentration of it is 0.1. This is the actual example that was in the test as well. You guys put. So before it dissolves in water, well, it hasn't dissolved yet, so it hasn't got any of the product. After it dissolves in water, this is concentration in molar. After it dissolves in water, it's completely dissociated, so there's none of it left. And you have 0.1 molar of each. Does that make sense? You don't have it's not 0.05 and 0.05 equals 1. It's 0.1 of each, because this splits into 2. And so it's because it's split into 2, and you have one of each. You comfortable with that?
Yes. I understand, but still kind of weird.
It is weird. No, it is weird. It's really that you have they're pairs of the whole. I guess it's like if you have 1 apple and you split that 1 apple in half, well, you've got 2 components of it. It's still got those 2 components, and that's effectively what you're doing. You're splitting it down the middle, and the mass is smaller. The mass is smaller. This is smaller than that, so the mass is smaller, but the number is the same, because you just split it in 2. So when you split an apple into 2, and you've got half 1 and half 2, well, each of those is 1 unit. So you have 1 apple splits into 1 half and another half, and each of those halves is 1 half. Well, this is what it is. You have 1 unit splits into 1 half and another half. And they're lighter because they're part of the whole, but the number of them is the same. It's the same number. So afterwards, you have, so that's where we're up to. This is all on the same line. And so what do we want to measure? Well, we want to measure the hydrogen ion concentration. And you see that it's just the same number. So if given a strong acid, because it 100% dissociates in water to proton and the anion, the concentration of the strong acid that you began with is going to be the concentration of hydrogen ions once it gets dissolved in the water. And so now we know the hydrogen ion concentration. So we want to know the pH. So we just take the negative log, and that will give us pH equals the negative log is 0.1 is 0.0, and that's the pH. The pH of a strong acid solution of hydrochloric acid is 0.1 molar hydrochloric acid is 1. This here should always be in molar. Always converted to molar. So if I was to say to you 250 millimolar hydrochloric acid, what I'm saying is 0.25 molar hydrochloric acid. This is really, really key. if I wanted to make this more complicated, I could say that I have a 0.2 molar hydrochloric acid, and I have 500 milliliters. And then if I add in 500 milliliters of water, then it's going to, I've now diluted it, and it's now 0.1 molar. So with a lot of the questions, especially the higher mark questions, I'll give you guys a couple of easy ones where I just say, here are the numbers, feed it into the equation. But there'll be a couple of harder ones where I say, you've got 2.2 molar hydrochloric acid, and this is the volume you've got. And remember, molar refers to a concentration. It's not the total number of moles in there, it's the total number of moles per volume. So if I've got 0.2 molar hydrochloric acid, I've got half a liter of it, and I add another half a liter, I've diluted it in 2, I've got 0.1 molar of it now. That's strong acids. Strong acids are easy. So the example with H2SO4, this is just easy. Whereas the rule with this, whatever the concentration is in molar of your starting strong acid, that'll be the concentration of the hydrogen ions, because it goes completely, it dilutes completely. What it will be, if it was H2SO4, it would just double, because there's 2 hydrogens to be released. So it would be you would have twice as much, and then the hydrogen, you'd be finding the hydrogen ion concentration of this one, which is going to be a difference. You've got more, so the pH is going to be lower.
Hydrogen not have its units.
You mean like this?
Yeah.
Oh, well, no. What it would be is that it would be that.
Okay.
That's what it would be. Yeah. Because H2 would refer to it's bonded, so it's like a hydrogen gas. Whereas it's not that it's bonded hydrogen gas; it's that you have 2 hydrogen ions. Yeah. Something which I should have, a small backtrack. I should have mentioned the scale of pH. How long have I been? A bit saying? Okay. I'm just going to finish explaining the scale. Well, you can go, but I'm just going to what you're going to be missing is just that I'll be explaining the scale where you have a high pH, a low pH, or a neutral. And so the say that's all I wanted to say is that as the concentration goes down, the pH goes up, or conversely, as the concentration goes up, the pH goes down, because it's the negative log, and you're flipping the sign. Whereas this is going to be H plus. It's going to be times very quickly. 1.0 times 10 to the negative 1. This is 1.0 times 10 to the negative 7. This is 1.0 times 10 to the negative 14. And so as the negative numbers, the negative powers get bigger, it's actually describing less hydrogen. And so when you find the pH, you take this power and bring it down, and then you find the negative log, you flip the sign. And so it's backwards. It's backwards because you're actually describing a smaller number when you take the negative log. And that's, I was hoping to get onto weak acids, but I spent 15 minutes trying to search for a marker this morning. Yeah, next I'll move on to weak acids, which just follows what I did for KW. You'll notice that was just like when you work out weak acids, except we're just going to do the H and HA equals H and A minus, and then move on to buffers with the Henderson-Hasselbalch equation. But that covers like the introduction to this section.